Okay, good afternoon, and let's continue with our discussion of resistor applications. Okay, so we've studied resistors, resistive circuits, few analysis techniques, and then we started going into applications of resistors. One of the most common application of a resistor is in a series resistive circuit for a voltage divider network. So this application was where we have a single source, single voltage source, and we're trying to obtain different voltages from our batteries or from that source. Sorry. So make sure right section. Yep. Okay. So in this case, we have a 9-volt battery, and one of the examples I also gave was we could have a network of 9 different resistors, all with the same value. 2, 3, 4, 6, 7, 8, 9. And you could connect it to that single battery and obtain a variety of output voltages. So voltage across, if all resistors are the same value, then they drop the same voltage across itself. If it's 9, then it's dividing that 9-volt battery into equal parts. So all resistors will have 1 volt across them. And we can take any combination of these in order to find or to obtain any combination of voltages. So we can obtain 2 volts, 3 volts, 4, 5, 6, 7, 8, 9. Right? 9 different combinations. You can have any voltages that we want. So that's a voltage divider network. Here it's from 18 kilo ohms and 22.5. We saw this in the previous example where the combined effect of 18 and 22.5 gives us a 10 kilo ohm RTH, Thevenin resistance, and the 9-volt source is now providing us with 5 volts. And that would be across the 22.5 kilo ohm resistor terminals A and B. This symbol, by the way, stands for equivalent, in case you haven't been told before or notified before. 2 lines is equal, 3 lines is equivalent. Okay. So other applications, one of the most common applications is in electronics amplifiers, specifically for biasing of transistors. Transistors is something you will learn in EE 315. And those are 3-terminal semiconductor devices. We don't look at those in 115, right? So 300 level class you'll be taking in spring. And we use voltage divider network at the base on the left side of the circuit, which is here, in order to provide a specific voltage going into the input terminal. So this is our transistor. This is just for informational purposes. This is not something I'm going to test you on, but this is known as a bipolar junction transistor, BJT. Has 3 terminals: collector, base, and emitter. So depending on the configuration, one of these terminals is common to the input side and the output side. In the common emitter configuration, the input is going in here, and the output is taken across here, collector and emitter. Okay. So now if there are 2 sides to this electronic device, then we need 2 separate power supplies, right? In a lab bench, you have easy access to two separate power supplies. In portable devices, not so much. Okay. And so a very easy way to get multiple power outputs is by using resistive voltage divider circuits. And so we use two resistors in a series configuration, and we obtain a Thevenin equivalent going into the base side. And so here, the voltage divider is comprised of the 20 kilo ohm resistor plus minus, you're applying 20 volts. Sorry, it's not 12, not 20, sorry, it's 12 volts. So you're applying 12 volts between the two terminals. And this is 20K, and this is 3.6K. Okay, so the midpoint in the middle, you're taking the voltage across the 3.6 kilo ohm resistor. If you measure that voltage, it's around 1.83 volts or less. Okay, 1.83 volts or less. And that's the typical configuration of these biasing circuits. So we have one voltage source, 12 volts. It applies a voltage called biasing voltage on the output side as well as the input side. But on the input side, we use a combination of two resistors to obtain a slightly smaller, sorry, not slightly, a smaller voltage. Okay. And so that's an application. That's a very common application of resistors. Okay, that's a very common application. Thevenin resistance can be determined on the input side, because for Thevenin resistance, what do? We connect or short out the voltage source which then goes to ground, right? So we are trying to find the Thevenin circuit between these 2 points. Then the 20 kilo ohm and the 3.6 kilo ohm resistors are in parallel. And so the Thevenin resistance, as looking from the perspective of the base terminal from the left, will be 20 in parallel with 3.6K. So again, base building off of the previous concepts, the same thing. We have two resistors, both end up in being parallel, and so the Thevenin resistance between those terminals is those two resistors in parallel, gives us a value of 3 kilo ohms. Let's take a pause and let me know if you have any questions. Just as FYI, we are only concerned with these two resistors. We're not worried about these. Okay. All of that is not part of this course. This is simply to show students that even something as simple as a resistor finds application in higher level circuits. Okay. Any questions? All right. The other place where you can find them is in op amps. How many of you have heard the term op amps before? No? Okay, great. This is your introduction to op amps. So op amps is short for operational amplifiers. We'll study them in this course. In E, students also study them in circuits 1. Okay, so op amps are comprised of numerous transistors and numerous resistors configured in a amplifier configuration. Very powerful microchip, very powerful system. But in circuits 1 and in circuits and electronics 1 for CP majors, we study op amps, not the internal circuitry, but we study op amps as a building block. Okay, we use op amps as building blocks to build larger circuits. Okay, so in this case, we have an op amp. The op amp is symbolized by this triangle. It has two inputs, an inverting input and a non-inverting input. Inverting input is marked with a minus, non-inverting is marked with a plus, and it has one output. The name op amp or operational amplifier came about because these kind of amplifiers are used for a variety of operations. Mathematical operations like addition, subtraction, differentiation, integration, comparison, as comparators, hence the name operational amplifiers. We use them for filtering, active filters. There are many other applications, unity gain buffers, and then voltage followers, which we'll look at in just in the next few lectures. Okay. So in these kind of op amps, we need biasing resistors and similar topology right here. You have a feedback resistor RF and you have a resistor R2. That V1 voltage is biasing the op amp in the negative terminal. You can see the minus sign and applies the same voltage division principle. Okay, voltage across R2 is the one that's being set up and going into the op amp right here. And so V1 is R2 over R1, I mean R2 over R2 plus RF times V out. Okay. There are many other things regarding the op amps, and we'll look at all of them. But right now we just focused on the application of the resistors. Okay. So again, same application, voltage divider network provides a biasing voltage that goes into the op amp, which allows us to create a variety of circuits using that one single device. The other application, again, similar to voltage division principle, is in the oscilloscope probe. So if you have used the oscilloscopes in the lab and you have used one of those oscilloscope probes, you'll see that a regular BNC cable simply has a connector, whereas an actual oscilloscope probe that comes with the oscilloscope has some circuitry built in at the base, right, where it actually connects to the oscilloscope. So the circuitry inside it is this. It allows us to step down any voltage that goes in by a factor of 10. And hence, that probe has a symbol called 10x on it. How many of you recall that? Have you used oscilloscopes in the lab? Right? So if you use a regular probe, the regular probe is simply 1:1, does not have any multiplication factor in there. If you use an oscilloscope probe that has a 10x or 100x setting on it, then the mechanical switch or the manual switch on the end of the probe, those settings must match the settings that you set on the oscilloscope itself. If there's a mismatch, your answers on the oscilloscope will be multiplied by 10. So instead of measuring 5 volts, you'll be measuring 50 volts. If something like that does occur in the lab, 100% is that there's a mismatch in the settings in the oscilloscope and the manual switch. Okay, that's something to keep in mind. But inside it, all it is a simple resistor. The resistor drops a big chunk of the voltage across itself. The ratio of that resistor to R2 is 0.1 or 10%. Okay, the ratio is 10%. So if you send in 100 volts, you'll be measuring at 10, right? So your range of measurement increases. If your oscilloscope is designed to measure up to 20 volts, but if you use a 10x probe, you can measure all the way up to 200 volts. Technically, all these oscilloscopes that we use in the lab benches, they can measure up to 300 or 400 volts. It'll be listed in their specifications as well as on the front panel. So don't do this, but technically you could take a probe, put it on 10x mode, and you could possibly stick it into the power outlet. Power outlet goes up to, anyone? What's the power? What's the voltage of the power outlet? 120 volts. Only one student knows. I think we talked about this, didn't we? So 120 volts RMS, peak to peak, is almost 340. Okay. √2 times RMS gives us one peak of the AC signal. So it's 169 volts in one direction and 169 volts in the other direction. If this oscilloscope can handle up to 400 volts using a 10x probe, you could potentially stick that probe into the power outlet. But again, don't do that. Not unless you are willing to replace the oscilloscopes. Okay, so that's the other application. So anytime we need a reduction in voltage or a division of voltage, that's where resistors find application. Okay. Lastly, we have this kind of circuit where we are trying to add two signals, meaning two different voltage sources, and we want to have a different ratio of addition of both of these voltage sources. So we can use resistors for that. So the weighted voltage summation using resistors. It's again something that is used commonly in digital circuits. Okay. So if you want to add two voltage signals in a 2:1 ratio, in this case, the requirement is V1 plus 2V2. So V2 must be twice as V1. If you apply superposition, we can see that V1 is going to be, not V1 is going to be, if you apply superposition, your circuit looks like this. This is your V out from the midpoint. And this is V1. If you do V2, again, the same thing. But now, R1 is connected to ground. And you're taking the output across here. Okay. So if you do superposition, you obtain this equation. If you take the ratio of the two signals, R1 plus R2 cancels out, or you have left is 2, where the ratio of R1 to R2 should equal 2. So if you choose R1, sorry, if you choose R2 as 10K, you can obtain R1 as 20K. Anyway, that's again a very simplified application for a resistor. Again, same principle. We're adding up the voltages. You've seen that before using superposition, Thevenin resistance, Thevenin voltage. Okay. All right, we'll end class here today. We'll pick up here again on Wednesday. We'll look at R2R ladder networks, again, using resistor applications. And then, yeah, then we continue on from there.